Okay, go.
All right, perfect. Hi, everyone. My name is Kevin. I'm the co-founder CTO of Tecton. So very nice to meet you all. And before I start sharing my slides, a little bit of background. Before I started Tecton, I was at Uber working as a tech lead and engineering manager on Michelangelo, the machine learning platform over there that basically all the data scientists and ML engineers and whatnot use to drive basically all of the ML use cases of Uber. Many of those are probably pretty obvious, like ETA predictions, safety predictions, dynamic pricing, fraud, all of that type of stuff. And a lot of the lessons we've learned there, we've spun out to build Tecton, which is a feature store company that I'm going to share and talk much more about in the next 60 minutes. So let me start sharing. I hope that's coming in okay.
Yeah, perfect.
Perfect. So specifically, what are we going to chat about in the next 30 to 60 minutes? I'm going to talk a little bit about what is operational ML and how is it different to analytical ML. Then I'm going to chat about why is it so hard to develop and productionize an operational ML application? How are feature stores the missing link here? Then I'm going to go through a couple technical sections where I explain what are actually the technical problems underneath the hood that a feature store solves. What are the organizational challenges a feature store solved? And then how can you imagine you'd use a feature store to begin with? And with that, let us dive right in. First off, let's look at what's the difference between operational ML and analytical ML. Analytical ML is oftentimes more obvious, it's more commonly used still if you look at large enterprises and whatnot. Analytical machine learning happens when you've got a human in the loop who looks at dashboards or looks at reports. Common examples would be dashboards that show you a sales forecast or reports. Or it may be a model that once a week predicts who are the users of your website who are most likely going to churn out. And then you've got somebody on the marketing team or whatnot who receives that email list and then sends out promo emails or something like that to the people. And so very often these types of analytical ML models, they're just being executed on like a batch cadence once a day, once a week, once a month, however frequently it is. And then they feed into a system that a human uses. Now that's very different to operational machine learning, which drives end user experiences where you require mission critical SLAs where there's no human, at least from the company, in the loop, and you directly impact the user's experience. So you need to act within a couple of milliseconds at most. Common examples that we find in the wild are fraud detections, real-time pricing, recommendations, all the type of stuff that I mentioned earlier that we did at Uber and that we now see other companies very widely employ. So let's look at why it's actually so hard to develop and deploy these operational ML applications. One of the main reasons for it is that an ML application really consists of 3 different artifacts. You've got an application itself, which wants to make a prediction. You've got a model that does make a prediction. And then you've got features or data that feed into the model that does make the prediction at the end of the day. So let's motivate this with an example, which could be a fraud prediction use case where of a credit card processor. So you've got a backend service, like a microservice, whatever it is, that will be your application, which receives a transaction that's coming in and that has to make a decision. Do I want to let this thing pass or do I want to reject it? How does this application do it? Well, it needs to talk to a model which looks at all the available data and then makes a prediction on whether this is likely to be fraudulent or not. And then, of course, this model doesn't just look at the incoming transaction, but it looks at a lot of other data, a lot of other features, what is typically referred to with machine learning, to getting some echo here.
Yeah.
They're usually considered undruggable by traditional small molecules. And a promising new class of drugs is based on large biomolecules.
You're helping me, Hendrik.
I'm trying to figure out, but everyone seems to be muted, so I'm not entirely sure where it's coming from.
Such drugs are called biologics.
I see Sam. Sam is lighting up. Here we go. Okay, we're back. All right, let me just start from scratch. Okay, so the model that makes a prediction on whether this is a fraudulent transaction or not requires access to or needs to look at all the available data. besides just the transaction that came in. So for instance, how many transactions has this user made in the last 1 minute, in the last 7 days? How many transactions has this user ever made on this platform? So all of this is what's in ML terms called features that feed into the model that the model then uses to make a pass, no pass prediction. Now, all of these artifacts, the application, the model, the features need to be developed and deployed in tandem, which is really, really challenging as of today. For applications, we've kind of nailed it by now. We're pretty good at it. We've got our CI/CD pipelines, our DevOps pipelines, which take your code from a GitHub repository, bundle it up in a Docker image, and then run it as a Docker container on your Kubernetes system typically. So that's not that hard anymore once you've got all the infra wired up. For models, we've gotten much better at it too, where we know how to, in a Jupyter notebook or in some other data science environment, train our models, which produces an artifact. And then we now, using MLOps pipelines or even your existing DevOps pipelines, we know how to deploy this model artifact now behind an API endpoint that can make predictions. But when it comes to prediction, to features, that's still a very, very hard part, because typically the way this works without a feature store in most organizations is that you have a data scientist who gets a raw data dump and maybe works in a CSV file or directly loads raw data from a data warehouse like your Snowflake or Redshift, or fetches some data from a data lake. And then in your Jupyter notebook, you do some Python-based data wrangling. You clean some data, maybe you aggregate some data, until you eventually have your clean, pristine data frame that you can feed into your ML training algorithm. Now that's nice, but the challenge is that once you've got this model that you're happy with based on some back tests that you ran and whatnot, you want to put this model in production. And in production, you want to be able to serve feature values so that your model can actually make a prediction. And that's where things get tricky, because what you typically see today is that the data scientist now works with ML engineers or data engineers who end up re-implementing the feature transformation code that does the data cleaning, the data aggregations, and all that stuff in a production-ready language, whether it's Java or whatnot. Maybe they run it on a production-grade data processing system like Spark or Flink, and then they need to take this output of these data pipelines, store it somewhere where you can later on pick it up. And I'll go into more technical detail here in a second. But you can imagine that takes a long time, typically. And that blocks the progress of the data scientist who's just trying to develop an ML app and get it into production. And so the missing link here is the feature store, which basically solves this problem and makes it much easier for data scientists to develop new features and to get them into production. So let's double click on what is this feature store thing. It's really the interface between the data and the models. So it's the system that connects to your batch data sources like your data warehouse or your data lake, and to your streaming systems like your Kafka topics in your organizations, your Kinesis streams, that type of stuff. Then it is able to process the data and make it available as features at low latency and high scale for your models running in production, and in large scale at batch for your model training pipelines that want to look at a ton of historical data, want to know what did the world look at any given point of time in the past. So you can train a model on the states of the world of the past. The data scientist uses this feature store to define new features, to deploy them to production, and then to share them as well with other data scientists for different use cases. So let's double click again and look at, hey, what are actually these hard problems? Like, why do I need a feature store in the first place? Or what would a data engineer do without a feature store? Well, as I mentioned now, the raw data could come from a variety of different batch data sources or streaming data sources, or even from real-time data sources, which it's typically the data source of the request that's making a prediction. So you could imagine like the current GPS location of a user who is using your application. In the moment where you're making a prediction, you may actually, as the backend service, receive that GPS location from your app, and that's now a real-time data source. So having to juggle these types of data sources, batch, streaming, and real-time, is hard for a variety of reasons. So let's first look at a very simple use case. Imagine again for the fraud use case, your model wants to know how many transactions has this user ever made since the dawn of time. Well, in the most naive implementation, your model backend, your application, could go to the data warehouse directly and submit a query. Nice little select and group by over all the transactions that have ever happened in your organization. And as you can imagine, that's going to take forever, minutes, hours, maybe longer than that. And your fraud detection backend can, of course, not wait that long to make a decision on whether it's going to reject or allow this transaction to go through. So for all the software engineers in the room, they probably know, well, I probably need to cache something here somewhere. And so that's exactly what would happen. You have to now decouple the feature calculation from the feature consumption. And so instead of having the backend go straight to the data warehouse, you know, typically have a feature calculation job which runs based on a trigger and calculates new feature values and stores them in a production store that your model backend is able to then fetch the feature values from. This production store is typically one that is that you'd commonly find in operational environments. It's typically a key value store that's is able to support really, really low latency requests at really, really high scale, like your Cassandra, your Redis, your DynamoDB. These types of stores are commonly used for this. And now the tricky thing with this is that you have to figure out how frequently do you want to compute and pre-compute these feature values. Do you want to run a batch job once an hour, once a day, once a week? Or do you want to run a streaming job against a streaming source that updates the feature values whenever a new event shows up? It's not a trivial decision to make, because there is a trade-off inherent here, which is the trade-off between the feature freshness and the cost efficiency. Now you can imagine if you run this pre-computation job just once a week, then your feature values could be as old as 7 days. For a fraud use case, that's not going to cut it typically. But if you run it every 1 minute or even faster than that, then you typically and oftentimes have to pay a lot more money. And so you have to be able to figure out what's this optimal trade-off that actually makes most sense for your ML use case. And of course, all of this gets really hard and really fun when you need to combine batch data sources, streaming data sources, and real-time data sources. And so this is like a fairly realistic data flow diagram that shows how these types of systems are then oftentimes built in the real world, where you've got streaming systems that process data from the stream, batch jobs that process data from your batch source, and then you combine all of that in with the prediction request data to eventually generate a feature vector that your model is able to make a prediction on. So all of that takes a long time and is very hard, and that's what a feature store helps you do automatically. Now, another problem that you typically run into when you try to solve these data problems for machine learning is that you want to avoid what's oftentimes referred to as training serving skew. And this is what happens when you have different implementations oftentimes between the training environment and the production environment. Remember this example I gave earlier where you have a data scientist working a Jupyter notebook, they do their data cleaning, their data preparation, then train their model. And that data scientist may now hand it over to a data engineer who may implement a completely different pipeline in the production system. So now you end up with two different implementations. And you can imagine that if those deviate even slightly, then you will introduce train serve skew, where your model is trained on data in a view on the world that it will never see as such in the production system. So your predictions are likely going to fall off the cliff. A common example that I've seen happen frequently is that you may have null values in your training data set. And so your data scientists, when they prepare the data set to train the model against, they may fill in those nulls with average values. And in the production implementation, maybe a null is filled in with a 0. And of course, the model is now not trained to ever look at zero values. And so when it encounters a zero value in production, makes a prediction, you don't know what it's going to do. And likely the performance is not going to be what you expect. And these types of problems are quite hairy to identify and to debug. So the right way to solve this and prevent this problem is to have one unified implementation for training and for serving, so that these types of inconsistencies cannot happen. And a feature store allows you to do this. Another pretty gnarly introduction for train serve skew are timing discrepancies. I'll just go through this really quickly. This is like an Uber Eats example where you have a backend that makes a prediction. How long does it take for your Uber Eats order or your DoorDash order to arrive? And it would typically look at one feature value, which is the trailing 30-minute order count in a given restaurant, because that's a proxy for how busy the restaurant is. And this is how you see it develop over time. Now, in production, you would typically not calculate this every single millisecond, but you'd buffer it, and maybe every 10 minutes or 5 minutes you update this value, and so you'd get a function that looks kind of like this. However, at training time, you would actually have the compute resources available to calculate the perfectly accurate 30-minute order count for any given historical order that was made at a restaurant. So your model would train on a distribution like this, while the model in production would have to make predictions on a distribution that looks like this, the blue line here. And as you can imagine, your model is likely now not trained to work with the noise that would expect to find in the production system. Again, leading to this train serve skew that is very hard to identify and very hard to debug. And then finally, another good source of train serve skew is data leakage, where when you generate the training data set, you introduce data from the future that you would never have access to at that point of time when you actually make the prediction in production. Favorite example, again, from the good old Uber days is, imagine you want to predict how long does it take to travel from one city to another, from Berlin to Munich, say. If you look at all the historical trips, a very useful feature may be, hey, was there an accident on this trip? And then that's probably going to indicate that the trip is going to take longer rather than shorter. But as you can imagine, if you generate the training data set that way, and you have a feature which indicates whether an accident happened, that's not going to help you in production, because you cannot look into the future and know whether an accident is going to happen. The only thing you could look at is the historical likelihood of an accident to happen. And so to sum it up, a feature store allows you to solve all these data problems that I've just mentioned, where it sits on top of your data sources. It is able to mix and match them. It's able to serve those, pre-compute these feature values at the freshness that you desire. It then serves these feature values to your model in production at the scale and latency that you need. And it is able to make those feature values available to your training environment without introducing train serve skew. So you, as a data scientist, will be able to go to the feature store and ask, give me feature values for a given user for a certain time range, and it would provide you with data points of the past of what the world and these features look like at any given point of time in the past. Now, problem two is that ML teams today are stuck building these complex data pipelines. I've just explained, like, what are all the different hairy data problems that you have to solve. Without a feature store, a data scientist has to go to the data engineer and make their case, hope that a new feature pipeline is going to be put in the data engineer's backlog and eventually will be prioritized so that the data is available. Of course, this slows things down, and the data scientist or the data science team cannot quickly enough iterate on their ML use case. With a feature store, this problem is solved because the data scientist can just use the feature store to immediately create production-ready features, push them into production, and thereby really shrink down this iteration time to get from an idea to a system that's running in production that you can experiment with and try out. And you really want to get this iteration loop and the iteration delayed down as much as possible so that the data scientists can experiment as rapidly as possible to eventually really optimize the model that's best suited for your use case. Then problem 3, again, if you have different data engineers who implement these data pipelines, what you typically find is that they may duplicate each other's work unknowingly oftentimes. There's no standardization happening. And as a result of the duplication, of course, you will be burning unnecessary amounts of money, because data pipelines actually oftentimes are really, really expensive. It's not just free software that's running, but it's actually processing oftentimes tons of data, which costs real money. Without the standardization, you've got another problem, which is the onboarding of new data engineers, or a data engineer leaves the company and nobody has any idea like how to maintain the data pipelines that this user has created in the first place. And it just overall throws these frictionful monkey wrenches into your data science org and slows things down unnecessarily. With a feature store, these features are managed as central data assets. So everything is contributed to the central catalog, to the central store, where other data scientists are able to browse for new features that they may want to use for their use case, contribute their features to, and so you can get this like internal network effect going in your company, where people can rely on each other's work and reuse what's already been created in the past. Final problem is that typically models do not break in production. It's the data that breaks for a variety of different reasons, where maybe an upstream data source is completely broken, where suddenly there's no data on your Kafka stream anymore or in your data lake. Or maybe you're actually encountering what's called actionable feature drift, where maybe the world is just changing, where you can imagine that for numerical features, maybe suddenly the mean or the standard deviation in production looks different to the mean and standard deviation you've observed when you trained the model. Or for a categorical feature, maybe the number of categories are drifting between what you're observing in production and what you've observed when you trained the model. Whenever that happens, beyond a certain degree, you want to retrain your model, because it's not used to seeing these types of distributions that it's now seeing in production. Another pretty gnarly problem is when you have feature subpopulation outages. It's an opaque term. What that means is that you can imagine you've got a model that's making predictions in the UK and it's making predictions in the US. And a certain feature has an outage, but only in the UK, not in the US. Now, if your monitoring only looks at the global data, the global feature distributions, then it's likely, depending obviously on the scale, that that feature outage for the UK is being drowned out by still good enough feature quality on a global level, given the size of what's happening in the US. And then finally, if there is an issue with the data, it's oftentimes not clear who's responsible for it, who should go there, who should fix the data pipeline. And as a result of that, again, it takes much longer for issues to be resolved than it needs to be. And with a feature store, it helps you identify these issues to begin with. It helps you identify, hey, when should you retrain your model? When is there likely an issue with the quality of your data? And bringing it all together, let's take a look again at the components of a feature store and the different interfaces of it. As mentioned, it sits on top of your raw data sources. It serves feature values to your model in production and to your data scientist who's training models. And it does that with these core components. One is the registry, which is basically the metadata catalog of the existing features. It has a serving endpoint that's able to serve those feature values to your production system or your training system. It's able to monitor the data, and it's able to run transformations as well as store the feature data. Now, what's super important about transformations and storage is that a feature store actually doesn't come with its own built-in transformation engine necessarily, or its own key value store or its own data warehouse. It is actually a layer on top of your existing data stack, on top of your existing data warehouse, your existing data lake, your existing, say, Spark cluster if you use this. And a feature store like Tecton plugs into your existing data environment and leverages the components that you have to solve these data problems for machine learning. Now, really quick to wrap things up, let's look at how do you actually use a feature store like Tecton? How do you define features, use them for training, and use them for predictions? The way you define them with Tecton is you define features in a very declarative way, meaning you describe them in files that you lay out on like a file system, which you'd of course back up in a Git repository in this very declarative way, where you use like a SQL transformation or a PySpark transformation or Python code to express the raw data to feature value transformation. You annotate it with some metadata around like what's the name of this feature? Should it be online servable? Should it be offline servable? And that's how you lay it out on disk. And that's the type of information that you then pass on to Tecton, so it knows, hey, what are the features I should make available in production? Then to generate training data, you would use Tecton's Python SDK in your existing data science environment, like your Jupyter notebook or your Databricks notebook. And you just go to the SDK and ask it to retrieve historical feature values for a list of features and a list of entities like your users or your events. And then you can train your model against it. And then finally in production, you'd be, as you probably expect, be able to ask Tecton to fetch feature vectors at low latency for a given user or for a given entity, and then make your prediction with it. Now, summing all of that up, how does a feature store actually help a team? What problems does it solve? Well, it all comes down to building more accurate models, because you can now leverage all of your onboarded data sources from batch to streaming to real time. As mentioned earlier, a feature store allows you to avoid data consistency issues and avoid this dreaded train serve skew. It allows models to be productionized in hours instead of weeks, because now data scientists are fully empowered to build these production-ready features immediately. And it brings DevOps-like best practices to feature development. As I just showed on the previous slide, these features are laid out as code. It's basically, like, we call it features as code, where they're laid out in a Git-backed repo, and you can integrate Tecton into your existing CI/CD pipelines to actually test and roll out these features in a very automatic way, the exact same way that we've brought DevOps best practices to the software engineering discipline. And turns out that Tide and Tecton have partnered up, and we've provided Tecton to Tide a little while ago. And here you see what the impact of it has been. Apparently, we've improved over 42,000 customer experiences for 42,000 companies, reduced the time to deploy models by over 50%, increased the number of features 3x, and saved 3 full-time employees and a lot of their time that they otherwise would have had to spend. Maybe Hendrik can say something about this.
Thanks a lot. Yeah, we started working with Tecton, and it's been actually a very great experience for us as well. But yeah, this is really, so thanks again, Kevin, for providing this presentation. I think this is a really good opportunity.
Just wanted to put this out there.
Okay.
just in case somebody wants to know, hey, how could I get started with a feature store? Just wanted to mention, hey, we've got an open source feature store out there called Feast with a limited feature set, and then a very full-fledged, fully managed cloud-native feature store, Tecton, that you could get started with at Tecton AI.
Cool. Thanks a lot. This concludes the first section, where we have this initial presentation that gives you an idea of like the topic of a feature store. And now let's go to the second section of you having the opportunity to ask questions to Kevin, who's really the expert on this field, has worked in this both in Uber and then also now started Tecton in order to do this full time. So probably the best person you can speak to on the topic of feature stores. So are there any questions already?
So I have a quick question. I'll just turn this on. There we go. Hi, so I'm Alex. I work at Tides. I've not actually been using Tecton yet, but it comes up in a lot of meetings and all this kind of stuff. So it's all very interesting. I was just wondering about kind of more complicated features. So, for example, maybe like word embeddings or like term frequency matrix type things. So, would you class those as features, or because I know that you can put them into pipelines, so maybe some people see them as models, but then I mean, then the interesting stuff, like, for example, if you're having loads of new words which aren't in your frequency matrix, if you don't have the frequency matrix itself inside Tecton, then you won't know that this is, the data is shifting around. So I was interested in your, opinion on more complicated, basically term frequency stuff, because this is something that I'm interested in.
Yeah, that's an interesting use case, and like we refer to this class of features as fitted features. And so what we oftentimes see and what we've used at Uber with our features, so there very frequently were embeddings, for instance, that we'd use to drive like restaurant recommendations and whatnot. And so there you now have the trickiness where you actually need to fit this feature itself on a training data set. And so you create this embedding vector, which you then store in the feature store, so you can actually serve it for training purposes and for production purposes. Right now with Tecton, we don't have built-in support for these types of fitted features. So what you'd have to do today is you'd have to actually create these embeddings or other types of fitted feature values outside of Tecton, and then push them into Tecton, so you can then later on retrieve them from Tecton for your training or serving purposes. So Tecton has this basically this push API where you can just put pre-computed feature values directly into the system, so you can retrieve it later on. Does that answer the question? Or
I think so. And then I suppose, because you have the stuff around monitoring, so would it like natively monitor that like you said, it is kind of a fit object itself, so it has some state which the data, the distribution of the underlying data could shift around. Would it know that the data is, the underlying distribution is shifting around of that particular group of words, or would you have to write your own code that kind of does that to check if the distribution?
If there's no native support for the format of the feature that you're putting into the feature store, it wouldn't know how to monitor it. And so you could imagine that, like for numerical values or for categorical, it's easy enough for it to figure out, hey, this is what I've seen beforehand, so I can monitor it easily. But if the user just gives me a data blob, I can serve it, but I don't know how to monitor it. And so over time, there could then be built-in support where Tecton now starts to actually be smarter about like sparse vector or other stuff where it can provide you with monitoring information. But it definitely wouldn't be able to do this for basically opaque data blobs where it doesn't quite know how to interpret it, where you as a user would only want to use Tecton for its serving and central storage capabilities.
Okay, but presumably it sounds like you're going in that direction.
Yes, we definitely want to build first-class support for these types of use cases over time.
Sounds good. Thank you very much.
Thank you. Are there any other questions one of you guys has already? Not yet. So please put them in the chat. And I was wondering, Kevin, could you maybe talk a bit about, you talked about this training serving Skew, and that is causing a lot of problems for a lot of companies. So how is Tecton actually able to try to address that?
So we address it by due to the fact that you as a data scientist give the feature transformation to Tecton. And so Tecton now has a guarantee that we take this feature transformation, this one and only feature transformations you've given to us, and we run it to generate both the training data and the production data at the exact same time with the exact same data pipeline. And so as a result of that, there is a guarantee that there's not going to be a logic discrepancy that we'd be introducing, because at the end of the day, it's the exact same code, because there's only one way for a user to give Tecton the code that describes the feature transformation. We'd be introducing a risk here if we said, hey, data scientist or user, give us one transformation code that we'd be running for training purposes and some other transformation code that we'd be running for serving purposes. If we did that, then it'd be very easy for you to introduce train, serve, skew caused by logic discrepancies. And then separately, the way we ensure that we don't accidentally introduce data leakage is that Tecton has this interface where you say, hey, give me a feature value for a given entity, for a given point of time in the past, and you provide a timestamp. And then Tecton internally actually associates every single feature value that it stored with the timestamp at which it was recorded. And so Tecton makes basically the product guarantee that it would never give you a feature value from the future. And so it avoids basically the data leakage problem.
Cool, thank you. Any other questions coming from the audience? What do you recommend for companies? Like, what is really the line of like, should we do this ourselves? Should we get some products? Like, are there specific like needs that are different maybe for companies? What is your view on that?
Yeah, I'm a big proponent of feature stores. This is probably not too surprising. So I think building it from scratch in-house is almost always a bad idea, and it's always going to take longer than expected. With the exception, like if you only had an extremely simple use case, say you only had batch machine learning, only against like a data warehouse with only a fixed set of features, and it's only a batch model that you're executing. So basically this analytical set of use cases I talked about in the beginning, then you probably don't need a feature store. You'd still get some benefits of it, but I'd just get started by implementing my own little data pipeline using the ETL tools that you already have in the company. But as soon as you start either having multiple data scientists in the organization, or you start going into the operational ML world where you run ML models in production, or you want to use streaming sources like Kafka or Kinesis, that's when you really want to use an existing feature store, so you don't have to build this thing from scratch, which again took us many years with a lot of engineers. And at Uber, it took us the whole system. We had a team of 40 to 50 engineers work on it over 3 years until we had something that's actually production ready.
Cool, thank you. I think Andre has a question as well.
Yeah, sure. Thank you. Thank you for the presentation, Kevin. I just have a quick technical question. So since we are focusing a bit on the streaming part, and what I read is that Tecton is using Spark structured streaming, how are you planning to solve the issue with more complex aggregations and near real-time requirements?
It depends on so on near real time specifically, what I think you're asking is Spark structured streaming itself has some limitations around the freshness, like you cannot get it down to milliseconds, for instance. And so how would you solve that problem with Tecton? Is that your question? If it is, then I'll answer. Yeah. Okay, perfect. Yeah, so that's
and
a great.
Also there are some functionalities that you can't do without incurring higher latencies.
That's right. And so those are two separate issues. So let's go through them one by one. The first one is, yes, Spark structured streaming has some latency constraints. Like typically what we've seen, you cannot, in a cost-efficient way, get Spark structured streaming down below, say, a minute type intervals, because it's at the end of the day processing data in mini batches. And so what we're working on right now, and actually very closely with Hendrik and Tide, is support where we use Spark continuous streaming, which has very different latency guarantees. And you would now be pushing actually a projection of raw events into the key value store. And then at request time, when you fetch a feature value, say like a 7-day click count or something like that from Tecton, Tecton would actually on demand now run an aggregation over a projected set of events. And then besides, now you may imagine, well, if I do this over a really long aggregation window, then that's just going to take forever, because the same thing as executing a query against the MySQL database or a data warehouse. And what's happening here is that Tecton will actually be compacting historical data every once in a while. So every night it would look at the historical events and then store in the online store what we call like a tile. And so at request time, you're now starting to run aggregations like your sum or count aggregation over raw projected events in your store and historical tiles. And what you get with that is actually extremely fast and extremely low latency and very, very fresh types of feature values. Obviously now at the expense of aggregation flexibility. Now you cannot do anything you want anymore, but you can cover basically the vast majority of aggregations like sums, counts, and all that type of stuff. And Tecton allows you to actually run on-demand transformations on top of aggregated feature values. So you can say, hey, Tecton, here's a Python transformation that I want you to execute on top of a combination of feature values, which allows you now to, again, fairly arbitrarily recombine the feature values afterwards on demand. I hope that made sense. That's a fairly complex topic. I'm actually going to publish a blog post about exactly the technical solution to this problem before the end of April. And hopefully we'll find a way to share that with you. I don't want to skip the second question that you asked, though. Like, there are definitely some inherent limits around the types of aggregations you can run. Like if you now want to say run a lifetime, say a unique count, a unique distinct count over the lifetime of a user against a stream, something like that wouldn't be possible very easily. You'd have to actually pre-compute this once a day or at whatever cadence you want, and you'd have to take the hit on the freshness unless you start actually blowing up the memory requirements of the data processing job. But this is now a rabbit hole that I'd happily go into offline.
Cool. I think there are I don't know, Patrick, do you have a question or was it just a comment that you made? Okay, probably just a comment. Daniel, do you want to raise your question?
Yeah, sure. Hello, everyone.
Hey.
See? Oh, yes. I just want to ask about, so at the end of the day, we're all trying to achieve, enriched data to make that model fly just as well in production. I'm wondering if introducing other data sources such as synthetic data, how helpful that would be. Do you think that we'd get more enrichment that way if we kind of pull it all in that direction?
Synthetic data sources. You mean if you added that to your existing data sets that you have available in your organization, if your model training would be able to pick up on some signal that then later on, okay. It's a good question. As you can imagine, as you probably know, like it all depends on like how accurate is this synthetic data? Like, is it actually going to match very closely the distributions that you later on will observe in production, or is it going to look different? Is it going to look different at on the outliers too? And you could imagine, let's say you look at the distributions of the data, now you create a synthetic data set that has the exact same, say, mean and standard deviation, then on average, I would expect that your model is probably going to be able to predict and do a better job. But of course, it now, with a higher weight, learns what the average point looks like, or what the average data point would look like. And your predictions on the fringes would probably now start to get worse because you hammer home much more like this average use case, basically. And depending on the business use case, this may be a good idea, or maybe it may be a bad idea.
Yeah, I mean, it's just an interesting perspective because I was looking at the way I see Tecton, because I do work on a lot of synthetic data myself. It's a similar, they're quite similar in what they want to do as their end goal. They just want to get that machine running much smoother, and stop it misaligning. And I was wondering, if both solutions could be looped together to somehow form a more complete model. But I guess that's a very sort of potential future avenue sort of thing.
Yeah, it is an interesting idea. Like in the future, where we definitely want to go with Tecton is we want this to be like the data platform for machine learning, and we want to solve all data related problems around ML. And so feature store is, the name itself is already way too limiting. Like I honestly really dislike the name, and we just coined it back at Uber, and now we've run with it because people know what it is. But the vision behind Tecton, and even what it does today, is so much broader than a feature store. It's really a data platform. And so things like fitted features should fit in there, helping you solve these problems that you're mentioning right now, where maybe synthetic data generation could fit in here, especially actually for the negative examples and for the outliers. I think that would be much more interesting and much more common. I think it's definitely an interesting future avenue to explore.
Perfect. Thank you very much.
Welcome.
Thank you as well for the question. Jimmy, you're next.
Sure. So I really just wanted to ask a question. This is mainly about change management and how, so you have a set of features deployed and then say one of those features gets redacted or privacy concerns around it, something like that. And then obviously you have a number of models that may be dependent on that. What does that kind of change management process look like? Or are you able to identify which features are used in which models, retraining, data versioning, that kind of thing?
Yeah, that's a great question. And the way we solve that is that with Tecton, you actually don't serve the feature directly in production. What you do with Tecton is, and I didn't go into the details here in the presentation, we call it a feature service. You could also think about it as a feature set. And so for any given model that you have in production, you would just declare a feature service, which has a name like model version 123, and it would point at a set of features and their versions. And so at production time, you would now not say, hey, Tecton, give me feature values for these 10 features, but give me the feature values for this one feature service, model V123. Now, what that allows Tecton to do is, and the user, when you now change one of those features, Tecton would notice that, hey, this transformation change is what we call a destructive change. And so the user will be notified before applying and rolling out the change that a feature service, and therefore likely a model in production, will be impacted. And so it asks you, are you sure that you want to execute this change? Are you sure that you want to destruct something that is running in production? Do you know what you're doing? And so you have to explicitly opt in. By default, it doesn't allow you to do this. And what you would typically do is, if you change a feature, you'd create a new version in Tecton, and you would create a separate feature service, like model version 2 now, and you would then change your production system to switch over from model V1 to model V2, and then afterwards go ahead and delete basically the old feature and the old feature service in Tecton. And so that allows you to basically have the lineage in place, be able to not by accident break a system that's running in production, and have full reproducibility and a version history of any of the changes that you've made basically to features that ever ran in production with Tecton.
Cool, makes perfect sense. Thanks.
Great.
Cool. Any other questions? Please come forward. In the meantime, Kevin, you mentioned very briefly that feature stores is maybe not the most well-defined term in itself. Can you maybe give some light into the different flavors of what this word might mean?
Yeah, in the most limited view of the world, a feature store is basically, like if you look at our friends at AWS, they have a feature store, or they call it a feature store, and it is at the end of the day a catalog and an interface basically on top of DynamoDB. And so it's now just a serving layer for features which you may want to use in production, and it gives you a catalog on top of that. So that is like the most retracted minimal set of a feature store, which is great for some use cases. It's great if you can run your transformations outside and you don't need the feature store to do it. It's great if you don't need the monitoring capabilities and a bunch of other stuff. Then there is another flavor where you have systems where you actually run the transformations themselves directly in the feature store, and you would run the feature store vendor's own internal implementation of the key value store or whatever data store they use. Versus on the other side of the spectrum, that's much more where we're at. Our feature store is pluggable with your existing data infrastructure. Like, we don't see ourselves as wanting to innovate in the data storage space or in the data transformation space. We much more want Tecton to be this layer this connects to your existing data processing tools, your existing batch storage, and your existing key value storage, and use those to solve the data problems for you. So it's basically, to put it very simply, the spectrum is extremely pluggable feature store that leverages as much of the existing data infrastructure that you have versus all-in-one black box feature store that comes with storage, that comes with transformation capabilities and everything built in-house, and it doesn't reuse anything or most of the things that you already have in your data stack.
Cool. Thank you. Are there any other questions one of you guys might have to Kevin? Otherwise, I think we'd close for today as well. No? Okay. So then, oh, one more, couple more. Just thank you.
Thank you.
Thanks a lot, Kevin. I really appreciated it. And I hope everyone has learned a little bit today as well. Again, thanks everyone for turning up, and see you next time.
Thank you. Bye-bye.
Bye.